computer. All right, take it away, Tricia.
Welcome everyone to our virtual February 2023 meeting. We have a very exciting show planned for you tonight. Welcome Shane Larson. Thank you so much for coming out. First thing, I would like to welcome all new members to CFAS. We appreciate your membership and we hope to provide you lots of astronomical value. As you can see tonight here, our agenda is as follows. We have Shane Larson presenting. I'm going to be presenting some club news. CFAS member Barbara Harris is going to be talking about the variable star of the month. And then Frank is doing member astrophotos. Okay, so a little bit here. We'll slide about Shane. I hope you guys can see this here.
Yep, all
I'm
good.
going to go ahead and hand it over to, all good. Okay, I'm going to go ahead and hand it over to Frank, so you can go ahead and introduce Shane.
Yes, we have Shane Larson back. He talked to us a couple of years ago now about gravitational waves, which is his area of expertise. Tonight he's going to talk about stars. So Shane Larson, if you don't remember him from last time or you're new to the club, is a research professor at Northwestern University in the Department of Physics and Astronomy. He is the associate director for CIERA. And if you think that sounds like a handy acronym for something that sounds pretty cool, it is. It's the Center for Center for Interdisciplinary Exploration and Research in Astrophysics. That's why they abbreviate it, CIERA. Professor Larson's research interests are primarily gravitational wave astrophysics and data analysis, but he is also interested in various aspects of cosmology, binary star evolution, gravitational dynamics in exoplanetary systems, and Earth's climate. So let me hand it over to Shane Larson. Thanks for being with us, Shane.
Thanks for the invitation, Frank, and everyone in the club. It's great to be here. It's great to be back. I did a virtual presentation. I guess it was probably still during the pandemic a couple of years ago, as Frank said, in gravitational waves, which is what I work on during my day job. I'm one of these weird people. I'm both a professional astronomer and an amateur astronomer. So coming and talking to amateur astronomers is something I love to do because I spend lots of time out on the telescope field with all y'all all the time anyways. And being able to kind of mix those aspects of my life is something that's very near and dear to my heart. And so it's fun to just come out and talk about the things that we do, talk about the things I work on, talks about the things I teach with folks who are curious and interested about it. So I hope you enjoy the presentation tonight. I'll talk for 45 minutes or something, and then we'll take questions at the end for as long as they're willing to let me. So let me go ahead and share some slides with you. So, I am a gravitational wave astronomer, but what my group specializes in is in the, or at least one of the things we specialize in, is the kind of evolution and changes that stars go through, in particular binary stars, over the course of their life. And so a lot of the things that I'm going to tell you about tonight are things that you may have heard about before, things you may have learned about if you've ever taken an astronomy course. But the tactic I want to take is one that I think as amateur astronomers, I hope you appreciate, which is this is all stuff that you read about in textbooks, but it's actually something we can show people to illustrate the story of the history and evolution of the cosmos when we're actually out on the telescope field with people. And so we're going to talk a little bit about all the stages of stellar evolutionary process in very broad strokes. And then I will endeavor to point out places or a couple of examples, by no means an exhaustive set of examples, of where and how you can see these things in the night sky. I always have extra reading for everyone at the end, places you can go read more and learn about all the stuff that we talk about. But there's a couple of resources right here on the first slide. There's my email address, s.larson, don't forget the period, it looks like a star there in the image, at northwestern.edu. That's there because we'll take some Q&A at the end, but invariably something will come to mind, or you'll have a question, or you'll know some 14-year-old who has a question that you can't answer, and you're always welcome to email me, and I can do my best to kind of point you towards resources or help you find stuff that will really get you going on your way about whatever your astronomical journey may be. Rightscience.wordpress.com there, that is my blog. It is a public-facing blog. I write about all sorts of things in astronomy, gravitational waves, black holes, SETI, whatever happens to strike my fancy. And as I tell people, it's meant so my mom knows what I do. So it really is meant for the general public. And if you're interested in stuff that I like to think about all the time, you can certainly spend some time there. And there's my social media links. If you tweet at me on Twitter, I'll certainly tweet back at you, and you can find a variety of things on my YouTube channel. So the beginning here is really the way many of us are used to the night skies, maybe not out our back doors. Many of us live in urban areas now, and light pollution is certainly stealing our night skies from us, even more so rapidly at an alarming rate lately. But for those of you who enjoy the summer months and go out to star parties, or in a couple weeks, those of you who are going to the Keys for the winter star party, we are faced by the true dark of night, and you can see the Milky Way and almost 10,000 individual stars that are visible to the naked eye. Now, they are all cataloged at this point in human history, all the naked eye stars. The Yale Bright Star Catalog did that, Doris Hofflet, a long time ago. But many of them have names, and they're familiar to us. And certainly right now, very prominent in the southern sky is Orion when it first gets dark. Even here in Chicago, I can see Orion, at least the main stars in Orion. And views like this, even just very narrow windows on the sky, have a lot to offer us when we think about how do we explain the story of stellar evolution to people. Okay, and so Orion in particular I like a lot because right in the sword of Orion, which is hanging down from the belt, the central star in the sword, as most of you probably know, is not a star at all. It's actually the Orion Nebula, which is a stellar nursery. It's a place where stars are born, and indeed through even our telescopes, you can see stars in the very young ages of their life. Similarly, up here in the shoulder of Orion is the star Betelgeuse. Betelgeuse is in the very end stages of its life, and those of you who pay attention to the news will remember that Betelgeuse has gone through some very dramatic changes over the last few years, which is engendering this question, is Betelgeuse about to go supernova? And in cosmic terms, the answer to that is yes, and in human terms, the answer is probably no. Okay, but we'll talk about these concepts all through the night tonight. Okay, and the point is we can ask questions about the stars precisely because of what you and I see when we go out at night. The stars are the most numerous object we can see in the night sky, and because of that, there's lots of examples of them. They show lots of variety and differences, and it's that variety and differences which allows us as astronomers and scientists to understand what stellar life is all about, even though the lifetime of a star is vast compared to the lifetime of any human, okay? And we'll talk a little bit more about that in a moment. So what kinds of questions can we today, as astronomers, answer about the stars? And the answer to that question is there are all kinds of questions that we can answer. They're the sorts of questions that people have wondered for a long time, but really in the last 100 or 200 years, with the advent of telescopes, the advent of spectroscopy, the ability to break light up into its constituent colors, and the advent of photography, which allows us to capture images of stars, capture spectra of stars, and then study them very carefully and precisely under controlled conditions. That technology is very enabling. And that's what has allowed us over the course of the last, couple of hundred years to figure out all the things that we know about stars, and certainly many of the things that we all kind of take for granted about stars when we've learned what we've learned, talking with our friends when we're out observing or reading about stuff in Sky and Telescope or taking astronomy in school. So all of these questions are questions that we have answers to. They are questions which some of them we understand very well, and some of them we just kind of barely understand, and there's still parts of the questions that we don't really know. And you and I could have a seminar like this every night for an entire year, and we'd not get through all of the things that we know about stars. So tonight, what I'm going to do is I'm just going to give you that high level, viewpoint about what's going on, and that will hopefully provide you some starting points for your own exploration and your own self-education about whatever it is about stars that might interest you. Okay, and perhaps give you a few tidbits you can tell when folks are looking through your telescope with you. Okay, so let's just start with, how can we figure out anything about stars at all? And when I ask people that question, I like to start with this slide, because this is something everyone's familiar with, whether or not you're an amateur astronomer, a professional astronomer, just getting into astronomy, or it's your very first astronomy club meeting, right? All of us are used to meeting all kinds of different people. Okay, and we meet all kinds of different people in our lives every single day. Okay, and if we were all in person, I would ask you, do any of you know any of these people? Okay, and I'm guessing the answer is no, because half of these people are friends of mine, and the other half of these people are random pictures I took off the internet. Okay, but it's important to establish at the beginning that you don't know any of these people, because the question I want to ask you is, could you take this set of pictures and rearrange them from youngest to oldest when you don't know who any of them are? And the answer to that question invariably is yes. You could probably switch these pictures around, and most of us would get this order just like I've done right here. Okay, and the answer to the question of how did you do that is that all of us have a very deep and intimate familiarity with thousands of people that we have met over our lives, and we've learned what the indicators are, what the things we can observe are that give us clues about how old a person is. We know what babies look like compared to what old folks look like. We know that some people are younger than other people, even when we can't see or know everything about the person that we're looking at, right? There's certain things that happen to people's hair when they get older. Their hair evolves in color. They begin to lose their hair. And even though I can't see this person's face, I can generally tell that they're older than this person to their left. Okay. And so, you and I could spend a lot of time making a list together of what are the indicators in this picture that made us put these people in the order that they are. And that lesson is the one that I want you to hold on to, because that's really the lesson that we use when we study the stars. I go out into the universe and I look at the sky, and there are lots and lots and lots of stars. And because I can see lots and lots of stars, I begin to group them together. I begin to see patterns about how they behave. I can begin to see patterns in their properties, how some are in some ways similar, in some ways different, how some are exactly alike, and somehow are completely different at all. Okay, so this is the Rho Ophiuchi complex, which is down on the border of Ophiuchus and Scorpius. You cannot see this magnificent complex with your naked eye. It really does come out in photography. But for those of you who are familiar with the area, this yellow star right down here, this is Antares. This is NGC 6121, which is a globular cluster that's right next to it. That's very easy to find, M4, as we call it. And then up here, it's this star. This is actually Rho Ophiuchi, the star that the complex is named after. Okay, so just like with the Orion field, this is a field where we can see a very robust population of stars, all of which exhibit different properties. And if we use those properties, we can use them to discover what the evolutionary history of stars in the galaxy might be. Okay. So I show this right before I show you the kind of master diagram that we're going to use for our tour tonight, because these kinds of complexes, these enormous gas clouds, are both the beginning and end of the whole story of stellar evolution. These are vast clouds of material in the Milky Way galaxy, indeed in every galaxy, but the ones we can see up close are in the Milky Way. And it is from these clouds that the raw material of stars actually comes, okay? And so this dark material here is just like the bright material. It's just not illuminated by stars, and it's not energized by stars. And so all of the nebulosity that you see in this image is part of the stellar cycle. Okay. Okay, so this is the master diagram. There are many versions of this diagram that you may have seen in your life or that you can find on the internet or in astronomy textbooks. The reason I like this one is one that's been around for a long time, probably since I was a student, is that this one shows that it really is a gigantic circle, okay? And there's two loops here. They both start and end here in the center, which is one of these gigantic molecular clouds that I just showed you in Rho-Ophiuchi. But many of the diagrams you see just lead you from stellar birth, which happens right here in the center, to stellar death, which happens out here at the ends of the arrows. But it really is this big cyclic procedure. And this is something that in my own professional research is really critical, because if you're asking questions about what were stars like in the beginning of the universe, it's very different than you ask what are stars like here in the Milky Way, which is very late in the universe's life. The way stars behave and evolve in the Milky Way is very different than the way they evolve and behaved in the very first galaxies, precisely because of the recycling that this big loop indicates. And so everything I'm going to tell you about is true in terms of stellar evolution, but we've really learned about it by studying the Milky Way and imagining this recycling process that I've showed you right here. So if I label this, each of these parts of the diagram has a name. It's a part of the stellar evolutionary process. And what divides the left recycling circle from the right recycling circle is really the mass of the star that's born out of the collection of gas and dust in the galaxy. So stars, when they're born, they're basically little gravitational magnets. There's clumps that begin, and they start gathering material to them through their self-gravitational pull. And a certain amount of material will glom onto you, and depending on how much material is around you, you will stop at different sizes. Some stars will be very tiny, what we call red dwarf stars. There's a lot of them in the universe. Some of them will be kind of average, not unlike our sun. Okay, and then some of them will be much, much larger, okay? And we can see examples of all of those in the sky. But what I'm going to do is I'm going to tell you this kind of general evolutionary story about how stars live and die. And the outcome, once you kind of get over here to the far left and far right of these circles, depends on how much stuff did you gather up when you were first born in the cloud of gas and dust in the center. I'm really only going to tell you about that story in the context of what happens to you at the end of your life, because that's what it primarily affects. But it does affect a variety of other things about your stellar properties, how bright you are, how hot you are, how fast you live and die, a variety of things. And we just don't have enough time to talk about all of the details. But the mass of a star when it's born is the thing that we almost always care about the most as astronomers. Okay? So let's start our journey here in the middle. We could have picked anywhere along either of these circles to start our discussion of what stellar life looks like, and indeed our tour through the sky. But let's start right here in the middle. Okay, so the middle, a cloud of gas and dust. We usually call these things stellar nurseries. And I mentioned a few moments ago the Orion Nebula. That's certainly the classic stellar nursery that you can see in the night sky during the winter. But you know, here in Chicago, we don't observe much in the winter. But although in Florida you may. But in the summertime, the classic stellar nursery is actually the Lagoon Nebula. Okay, so this is the southern sky. You're very near to the brightest part of the Milky Way when it's up in the night sky. We were just looking at the Rho-Ophiuchi complex, which is over here around Antares, but right over Sagittarius, if Sagittarius is a teapot, the kind of bright part of the Milky Way above it, right in there, there is an object that is a stellar nursery, the so-called Lagoon Nebula. So this is a classic color photograph of the Lagoon Nebula. It has a lot of intricate structure to it. It has a lot of bright regions where stars are illuminating it. And indeed, it has some of these kind of dark lanes through it that we saw when we were looking at Rho-Ophiuchi, which are dense parts of the clouds that are between you and the parts of the nebula that are being illuminated. Now, one of the things that our friends who don't look through telescopes or people who aren't amateur astronomers aren't used to is that when you and I go out and we look through a telescope, this isn't actually what we see, right? Most of our telescopes aren't large enough to actually put enough light on our eye to generate color. But nevertheless, when you look through a telescope at the Lagoon Nebula, it still looks very much like this. It just looks kind of black and white, particularly if you can filter it. Okay, so this is really what the Lagoon Nebula looks like when you look through a telescope. And the part that I want to draw your attention to here is this grouping of stars over here. Okay, so this is an overlaid, as we call it, open cluster. We're going to talk about open clusters here in a little more detail in a minute. But open clusters are the groups of stars that are born out of molecular clouds in the galaxy. They are all together because they were born out of the same molecular cloud, but generally there aren't enough of them that they're going to stay together for their entire life. Okay, they're far enough apart that they aren't seeing each other's gravity, and over time, over history, they're going to drift apart. But the important part is that they were all born out of the same molecular cloud, which means they have the same chemical composition and same stuff that they were made of. So when I look at stars like this, I can identify them and tell that they're related by using spectroscopy, breaking light up into its constituent colors to kind of tell what they're made of. Okay. Now, there are lots of famous examples of open clusters in the sky that we often show people. Usually when we're looking at the Lagoon Nebula or any stellar nursery, we're really looking at the nebulosity. That's what people are, all excited about. But there are other really fantastic open clusters. And so if we just kind of march up the Milky Way from the Lagoon Nebula, there are other examples of stellar nurseries, and then there are other examples of open clusters. So let me run up just a little bit up the Milky Way there. So right between Aquila, Ophiuchus, and Sagittarius is a very famous nebula called the Eagle Nebula. Okay, and the Eagle Nebula is probably most famous in people's minds for this Hubble Space Telescope picture. Okay, so this is, those of us who grew up in the Hubble era will recognize this. These are the so-called pillars of creation. Okay, so these long fingers through the nebula are places where stars are being born out of the gas and dust of the nebula. Now, this has recently come back to people's attention because JWST took a rather spectacular, one of its first light images was of the Eagle Nebula. And so you can see these pillars of creation by JWST. There are some very bright red regions up here. Those are regions where there's lots of gas and dust that's kind of been shocked together. And so it's very bright in the kind of light that JWST observes in. But you will see these kind of luminescent red points throughout the nebula. And those indeed are the brand new young stars that are being born out of the pillars of creation. One of the exercises we do a lot these days is put a Hubble picture right next to a JWST picture. And so this is the example of the pillars of creation oriented so they look the same. And the thing I want to point out here to encourage you to look at JWST and Hubble images together all the time is that you can see way more stars in the JWST picture than you can see in the Hubble picture. And the reason for that is that the Hubble picture is not looking at the sky with the same kind of light that the JWST picture is looking in. The Hubble picture is using light that you and I, for the most part, can see with our eyes, visible light as we call it. And in those colors of light, gas and dust block all the light from stars that's behind it. That's why the pillars of creation look dark. But if you look at the JWST image, they're looking at the sky in infrared light, in light that is way past red on the spectrum. It's so red that your eye can't see it. It's the same kind of light that thermal imaging cameras use and nighttime security cameras use. And one of the great lessons of astronomy is that every kind of light is useful in astronomy. And so when you look at the pillars of creation, that infrared light comes right through that molecular cloud. And that's why you can see so many stars in the JWST image compared to the Hubble image. And that's really quite valuable to us as astronomers because we're trying to understand things like how far away is the pillars of creation. We can figure that out by counting how many stars are in front of it compared to how many stars are behind it. We're interested in the stars that are just being born deep down in the molecular cloud, and we can see them much better in infrared light than in visible light. So as we get more and more images from JWST, they're going to be colored in ways that look familiar so that they look like pictures of the normal Hubble style pictures that you may have seen. But just always be cognizant that they're often showing you things that you can't see with your naked eye. So sorry, even with your unaided eye, with a telescopic eye, using light your eye can see. Okay, so if we march up just a little bit farther up to the, I guess it's the tail of Aquila, not the head of Aquila, there is a very famous open cluster there called the Wild Duck Cluster. Okay, so this is M11. You know, the debate we always have on the field when we observe this is, why do we call it the Wild Duck Cluster? There are lots of reasons and explanation people give, but, you know, all of these names were given in the 1800s typically, and so we just think it's their telescopes weren't as good as ours, and so they thought it looked like a wild duck. But it is an open cluster, a group of stars that were all born together. You can see many of them kind of have the same kind of coloration and kind of same size and brightness in the image. And these are all stars that were at some point in the past emerged, were born out of a stellar nursery. And they gobbled up a lot of the gas and dust that was in the stellar nursery. As stars turn on, they get very bright, their winds turn on, and they tend to blow away all the gas and dust that was around them, leaving the open cluster behind. And the Wild Duck Cluster is a really quite beautiful one to look at. People even with binoculars can pull this out, and it's really a very, very nice example of what open clusters look like. But this is, you know, an open cluster early in its life. The stars have just been born, you know, on relative cosmic scales. And over time, they are going to wander off and go lead their own lives in the galaxy, right? So what happens to open clusters after they're born is the stars, they're all traveling in different directions, and over time, they will spread out over the sky. And eventually, when we look at that part in the sky, we won't see an open cluster anymore. Okay, and so as astronomers, then we ask the obvious question. It's like, wow, could I find a whole bunch of stars at different places in the sky and ask the question, were these stars all born together? Are they siblings that are now spread throughout the galaxy and in different places? And the answer to that question is absolutely, we can do that, right? So the most famous example of this is actually in Ursa Major. Okay, so this is the tail of Ursa Major, the body and tail of the Great Bear. Okay, so the Big Dipper, it's up all year round. You can see it if you look at it in the northern sky. And these stars right here in the kind of diagonal part through the Big Dipper were all part of the same open cluster. They were born together, but now they've spread out in the sky so much so that they form a big piece of a constellation. They're not a little small cluster that I can look at through my telescope. How do I know they were born together? Well, I can look at their composition. They all look like they have roughly the same composition. I can look at their motion through the galaxy, and they all look like they came from a common point in the galaxy. So this kind of grouping of stars that we can identify this way are usually called a moving group. Okay, so if you look at Ursa Major, these red stars that I've marked here are all the stars in Ursa Major that are part of this moving group. But in fact, if you look at open clusters, here's 1, 2, 3, 4, 5, 6, 7, 8 stars in this moving group. But open clusters have way more than 8 stars. And so, being diligent astronomers, we can look around the sky, and indeed, we can find the other stars that belong to the moving group. The moving group is about 300 million years old. It's about 30 by 18 light years across, and the center of it is 80 light years away. And if I map it across the entire sky, you can see it includes not only the stars in Ursa Major that I just showed you, but all these other stars. There's a star over here in Lyra. There's a star here in Corona Borealis, a few stars here in Serpens, one in Boötes. I don't know if this is in Leo and Virgo, a couple over here near Orion and Taurus, and one up here in Auriga. All of these stars, I guess I should have colored these ones too, right? All of these stars are part of this Ursa Major moving group. Okay, they're a stellar stream, as we say, that has moved out through the galaxy, and this is where the body and structure of the galaxy comes from. Okay, so that's kind of cool and something I enjoy very much. And one of the things that we spend a lot of time debating whether or not it's possible, and we certainly have colleagues who work on this, is whether or not it's possible to do this exercise, not just for some random group of stars. Oh, let's find out if we can find the moving group that belongs to Ursa Major. But what we would really love to know is, where are the siblings of the sun? Can we find stars in the galaxy whose chemical composition looks just like the sun? And can we tell where we all came from when the sun was born? Okay, and that's kind of a neat idea to noodle around on in your brain. Okay, so stars are born, they're born in groups, they move out through the galaxy, and then they live their lives. Okay, and so in midlife, stars are just like me and you, right? Stars in midlife, they have a job, right? And their job is to get up every day and burn hydrogen into helium. That's what they do, okay? And so every single day, right, stars, that's all they do. They get up in the morning, they burn hydrogen into helium, and then the next day, they keep burning hydrogen into helium. And earlier I said, you know, how a star lives its life depends on how much stuff it had to start with, what its mass was. And so the reason that influences a star's life is because how much stuff you have is really your supply of hydrogen that you can burn into helium, okay? But it's also, the bigger you are, the faster you burn your hydrogen. Okay, so you live fast and you die early if you're a big star, because you just burn through that hydrogen as fast as you can because you're squeezing on it so hard deep down in your core. But most of the stars that you see in the sky are right in this kind of midlife thing. They're going to live like our sun for billion years, 10 billion years, and they will just keep doing what they do until they have exhausted that supply of hydrogen that's deep down in their core. Okay, now I'm not going to talk about that process. There's a whole entire talk we can talk about how stars generate their energy and what it means and how we know it. Okay, but that's what they're doing. The energy, the light from the stars is coming from this process of fusing, nuclear fusion of hydrogen into helium. Okay, but at the end of a star's midlife, right, they will eventually use up all the hydrogen that's deep down in their core. Okay, there's still hydrogen out in their body, but down in their core, they're going to use it up. And when that happens, they retire from this process. Okay, they move on to the next stage of their life, and that stage is usually what we call the red giant phase. Okay, now there are many red giants in the sky. There are red supergiants in the sky as well. Okay, but what happens is when the hydrogen burning stops in the core, it moves on to burning helium into other things. And what that usually does is it increases the energy that's in the outer layers of the star, and that causes it to swell up. Okay, so it's kind of what happens to all of us when we get old, right? We swell up to bigger than we used to be. And when stars do that, they get enormous. Okay, the sun, when it swells up to this size, will basically fill the space inside the Earth's orbit. Okay, so these red giant stars are enormous objects. They're not any more massive, but they swell up to this big size. And as a consequence of swelling up, they spread their energy over a much larger area, the surface of the star, and that makes them start to cool off. It's like spreading eggs out on your plate in the morning. It makes them cool off quicker. And it's that cooling that makes them very, very red. So there's great examples of red giants you can see in the sky. So if we go back to our Ursa Major chart where we were talking about the moving group here, we typically use the handle of the Big Dipper here to point to one of the most famous giant red stars in the sky, Arcturus, which is right at the base of Boötes here. Okay, and Arcturus is very red. Okay, when you look at it with your night sky, this is an artist rendition of what it might look like, but it's enormous compared to our sun. It's about 25 times the size of our sun. And I would have made the sun a color that we're used to thinking about, but it was hard to see against the picture of Arcturus. Okay, so the sun's this blue dot here, and Arcturus in its red giant phase has swollen up to be 25 times the size of the sun. And that's why it's very bright. There's a whole bunch of bright surface area on the star. When you and I look at the sun, we're seeing this much bright area, but when you look at a red giant, you're seeing this much bright area. And so that's why red giants typically look very bright. Okay. So this phase doesn't last forever, right? The burning helium is harder than burning hydrogen. Deep down in the core, this process kind of goes on as far as the star can. But for stars like the sun, they'll swell up to this red giant phase, and eventually they're just going to give up. Okay, they can't generate any more energy. They're not big enough to keep driving the fusion process in their core. And when that happens, they tend to shrug off. They throw off the outer atmosphere of the star. Okay, and when they do that, that becomes an object in the sky that you and I call a planetary nebula. So this is one of the problems with astronomy, is that we have weird names for things. So planetary nebulas have nothing to do with planets, right? They are called this because many of them, when you look at them through a telescope, they look like small round dots, which is what planets look like in small telescopes. And so when these were first being discovered all over the sky, this is why they called them planetary nebulas. They show a great diversity in shape, morphology, as we call it. These are all, intricate astrophotos of them, but you can see some of them are very round. Some of them have ring-like structures. Some of them have kind of elongated structures along a certain axis. And there's a lot of work in the professional astronomy community to try and understand why they have the varied shapes they do. We understand some of it, and others of it we don't understand. A lot of it has to do with the way the star is spinning. A lot of it has to do with the things that cause the star to change its brightness and change its behavior over its life. And Barbara's going to talk to you a little bit later about variable stars, and variable stars' fates may have great influence on the way they become planetary nebulas. The cool thing about planetary nebulas is that they're very short-lived. The star throws off this atmosphere, and there's nothing that's going to keep that bubble of gas and material that the star throws off from continuing to move out into the galaxy. And so the kind of typical lifetime of planetary nebulas, meaning how long could you see it in a telescope, is only about 10,000 years. Okay, so if you and I could go into hibernation and wake up 10,000 years from now and go to a Central Florida Astronomical Society meeting, the planetary nebulas that they were used to looking at would be completely different from the ones that you and I look at tonight. And that's because they just don't live very long in cosmic timescales. Okay. The most famous, probably one of the most famous ones, is the so-called Ring Nebula in Lyra. So this is astrophoto of it. The reason it's called the Ring Nebula, it's actually a bubble of gas. But just like when you're sitting out on the front porch blowing bubbles and you look at a bubble, what you see is the outer edge of it. But right through the center, it looks rather transparent. You can see people through it, the middle of it. And so ring nebulas are the same way. The edges of the bubble where you're looking through more material are the things that show up very readily. Okay, there's also a background galaxy here. I actually don't know the number of that galaxy, but I just noticed that here in this image. So this is what happens to stars like the sun when they die. Okay, but the reason I show you the Ring Nebula here is right here in the center of the Ring Nebula, you will see a star. Okay, and if you look at lots of planetary nebulas, you will see in the exact center of them a star. And that star is not a star that's in its midlife doing its job, burning hydrogen into helium. It's actually the skeleton of the star that created the planetary nebula. Okay, and this is something my group spends a lot of time studying. These are called white dwarfs. They are very dim by relative standards. They're very shrunken. They shrink down to about the size of the Earth, and they're very dense, okay? So this is what the fate of the sun is. The sun in 5 billion years or so will become one of these white dwarf skeletons. Now, this picture here on the right is actually of the star Sirius, but the white dwarf is actually the little small star next to it called Sirius B. Or those of you who have looked at this, this is often called the pup. You can actually see it in an amateur telescope, but you kind of have to really work hard to see it around the glare of Sirius, okay? So if it's clear tonight and you can get your telescope out, you can go out and see if you can see the pup. So the belt of Orion kind of points downward and to the left. It points right at Sirius if you look in that direction, okay? Now, this object, this white dwarf, is shrunken down to about the size of the Earth, but it typically still has a mass very much like the mass of the sun, okay? So the sun is much bigger than the Earth. Its volume is 1,000,000 times larger than the volume of the Earth. So if you shrink it down to the size of the Earth and keep its mass about the same, that means it becomes very, 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 very dense. Okay, and so white dwarfs are extremely dense. They're almost all, or the most common of them, are almost all carbon. And you and I have a name for dense carbon. It's a crystalline form of carbon that we call diamonds. Okay, now no one's ever been to a white dwarf. No one's ever drilled into a white dwarf. So it's unclear how amorphous or how perfect the crystalline structure may be. It's also unclear whether or not carbon has interesting forms that it could get to through astrophysical processes. But the density and crystalline structure suggests that this is the kind of thing we should have in mind. Okay. So there are lots and lots of white dwarfs in the sky, and that's because most stars in the sky are just kind of average run-of-the-mill stars, and their fate will be exactly what the fate of the sun is, okay? But what happens if you're more massive than the sun? Well, if you're more massive than the sun, you become a red giant, but when you get to the end of your life, you don't slough off your atmosphere. You suddenly collapse, and all of the material that was a part of you begins to fall inward towards the core of the star. There's a whole bunch of complex fluid dynamics that we're still trying to understand with computers. But what happens is this kind of shock wave of energy and particles like neutrinos kind of comes outward through the star as it's collapsing. And that blasts almost the entire envelope of the star outward into a nebula. Okay. And so what happens is that explosion is very, very bright. Okay. It is typically 10 billion-ish times more bright than the sun is. So for a brief moment in time, the explosion will outshine the parent galaxy that the star is exploding in. Okay, the last recorded explosion of this sort in the Milky Way was before the invention of the telescope. Okay, so we call these supernova. And so we haven't actually seen one of these in the Milky Way in modern time, but recounting of historical supernovas in the Milky Way say that they were bright enough to see during the daytime. So you would walk out, you're like, oh, there's the sun. Oh, there's the moon. Oh, look, there's the supernova. And that they were bright enough to read at night for a few weeks until they began to fade and the energy began to dissipate. Okay, so these are enormously energetic events, okay? And they leave behind remnants just like stars like the sun do when they die. Okay, so there's kind of two parts of the remnants that they leave behind. So if you move off the wing of Cygnus, okay, so this Cygnus is kind of coming up in the early morning right now, so you might have to wait until late summer before this gets high enough in the sky to see it. But many of you will have looked at this. There is an enormous complex right off the wing of Cygna that we call the Cygnus Loop. Okay, it has an eastern and a western part. Okay, so this is the easiest part to find. That star you see right there at the top, that's 52 Cygni, 51 Cygni. It's right in the middle of this part of the Cygnus loop, which is usually called the witch's broom, I think. Okay, if you just point your telescope at that, you can often see this. And if you filter it, you can certainly see it. Okay, and from dark skies, you can follow around and see all of this enormous shell that is slowly falling apart of gas and dust that was thrown off during a supernova some 10,000-ish years ago. Just like planetary nebulas, this will continue to expand and eventually dissipate out into the galaxy, but they live a little bit longer because there's quite a bit more material in them typically, okay? So this is a really fantastic example of a supernova remnant. And I'll show you one more here in a minute. I'll show you the Crab Nebula in a minute, which is probably the most famous one. But let's talk about what it left behind, okay? So when we looked in the center of the planetary nebula, we could see that white dwarf, that stellar skeleton right down in the middle. And so in many supernova remnants, we can find a remnant that lives down in the center. We have often looked for and not yet found the remnant of the star that caused the Cygnus loop. But in many supernova remnants, we can. Okay, so what is that stellar skeleton? Well, just like the white dwarf, it's about the mass of the sun, typically a little bit more, about 1.5 times or 2 times the mass of the sun, but it's very, very small compared to even a white dwarf, okay? So the scale that we talk about these things on is usually the scale of a city, okay? So if I were to take the city of Orlando and put one of these stellar remnants on the top of it, it would basically cover the entire city. Okay, it's about 12 miles, 20 kilometers across, and it's about 1.5 times the mass of the sun. Okay, this remnant is what we call a neutron star. It is called a neutron star because during the process of the explosion and the compression of material at the core, all of the atoms that used to make up the inner parts of this star disintegrate into their constituent parts. Neutrons, protons, electrons, all those particles you learned about when you took physics in high school or college. And then the energy and the compactness is enough that it drives all of the protons and electrons together. Okay, so that's something that we physicists call neutronization, the creation of neutrons, or inverse beta decay, if you want to impress your mom tonight with some fancy science lingo. And that takes and turns those protons and electrons into neutrons. So this entire thing is something that's like 1.5 times the mass of the sun. It's only the size of a city, but it's completely made of neutrons. And as you might imagine, an object like this has some very extreme properties. If I could put one of these neutron stars over the city of Orlando, and you were to go downtown and stand on top of the tallest skyscraper with a spoon and grab a spoonful of material, okay, so something the size of a sugar cube, and put it on your bathroom scale, the material that this star is made of, a sugar cube sized piece, would weigh 3 times more than the entire human race. It's very dense, and it's unlike anything you and I encounter or can easily make here on the laboratory, here in the laboratory on Earth, okay? The star itself is very extreme as well. The gravity on the surface of the star, right, is like 200 billion times stronger than the gravity that's holding you onto your seat right now, okay? You and I could barely walk on the surface, but if we could walk across the surface and we had the misfortune of encountering a cliff just 1 millimeter tall and we fell off that cliff, we would be traveling at 140,000 miles per hour by the time we reached the bottom of that 1 millimeter high cliff. Okay, these are extreme objects, but we know they exist. In all our studies of all the supernova remnants and all the stars in the sky, we see lots and lots of neutron stars. And so just like the story of we look at lots of stars to understand stars, we look at lots of stellar skeletons to understand stellar skeletons. And we've learned a tremendous amount about these neutron stars. Probably one of the most famous examples is at the heart of a supernova remnant called the Crab Nebula. So this was created by the supernova that happened in 1054. Okay, so that was some 600 years, 550 years before the first telescope was ever used for astronomy. And when they went and looked at where supernova 1054 was in the sky, they discovered the Crab Nebula. But what we know today is that if we look at the heart of the Crab Nebula, there is one of these extreme stars, a spinning neutron star, which is something that in astronomy we typically call a pulsar, because it's sending pulses of energy that we can detect on Earth. If we look at it in radio, and in the case of the Crab, we can also see it in a telescope. Okay, so I have a audio file of what the crab pulsar sounds like if you just play its radio signal through a set of speakers. Okay, so I'm going to play that audio file. Those of you who are listening on headphones, it may be really loud, so I want to give you a moment to just pull them out of your ears, and then you can hold it up to your ear at a level that's comfortable. But let me play that audio file for you. Okay, the Crab Nebula is spinning 3 times every second. Okay, so this is what the signal sounds like if I just stuff it out through a speaker. And it just does that all the time, right? It sits there all the time just sending out this signal. It sounds like the car you had, the first car you bought when you were in college, right? So so that's the signal. And so when we first detected these things, we didn't have any idea what they were. Okay, and we eventually figured out that they're these neutron stars and they're spinning very fast, and they've been a kind of interesting subject at the forefront of astrophysics now for 50 or 60 years. Okay, so here's a finder chart. This is again that Orion area that we showed right at the beginning. Here's Betelgeuse, and right above Orion is the horns of Taurus. Aldebaran's another red giant star you can see there, but right out near the ends of the horn is where you can find the Crab Nebula. The Pleiades and the Hyades are 2 open clusters that you can see in the same region of the sky. Okay. Now, that is not the only possible thing that can come out of a supernova explosion. Some stars are so big and the explosion is so powerful, it will take those neutron stars and it will crush them to something even smaller. So if I can take that neutron star that's about 12 miles across and squeeze it down to just 3.5 miles across, this will become one of the most exotic objects known in astrophysics, what we call a black hole. It's an object whose gravity is so dense, not even light can escape from it. Okay, and what happens beyond the surface of the black hole, we don't know, because we mathematically know what could happen, but we have no experimental way of easily probing it, because everything we know about the universe we learned by using telescopes. Okay, so these have, for the entire time I've been a professional astronomer, we've known they've existed, but they still today remain one of the most enigmatic objects in the sky. Okay. But as astronomers, it's our sworn duty to figure out everything we can about everything that is observable in the sky, and black holes are among them. So my wife is a president and CEO of a planetarium. And so I asked her, I was like, I'm going to give a talk, and I need to show people what black holes look like so we can talk about what astronomers do when they look for them. And she's like, sure, absolutely, hun. I can give you a picture as long as you give me the image credit. And I'm sure, no problem, I can do that. And this is the picture she gives me to show you what black holes look like. Okay. And, usually we laugh about this. Hopefully you're laughing at home, but it really is a serious picture because it illustrates the problem we have with observing black holes. All we know what to do is to use our telescopes, whatever telescopes they may be. But black holes don't emit light by definition. So the only thing we can do is look for things that do emit light and watch what black holes do to mess them up. Okay, so the classic example is again here in Cygnus. So right in the middle of the summer triangle, right near Eta Cygni, which is the center star in Cygnus, there is a black hole known as Cygnus X1. Okay, so this is the star hopping chart, because Cygnus X1 is not just a black hole. It's a black hole that's orbiting a companion blue star, and you can see the blue star in your telescope. Okay, it's the closest, actually it's not anymore, I should fix that. There's now a closer black hole candidate that we discovered with Gaia, but traditionally this has been the closest black hole candidate to Earth. It's about 5,900 light years away. Okay, and this is what we think the system looks like. About every 5.5 days, the black hole makes one complete orbit around its companion. They orbit each other. And the companion, because it's a bright young star, is blowing off a stellar wind, and the black hole captures that stellar wind. And as the gas flows down onto the black hole, that gas gets very hot. And when gas gets very hot, it emits X-rays. So Cygnus X1 is the first X-ray source we discovered in the constellation Cygnus, and this is one of the ways that we know there's a black hole. The other way we know there's a black hole is if we watch this star's motion very closely, we can see it wobbling back and forth on that 5.5 day period. Okay? So that is very briefly all of the links through this diagram of stellar evolution. Okay, the skeletons are down here at the bottom: white dwarfs, neutron stars, and black holes. And all the material that's thrown off, whether it's in a planetary nebula or a supernova remnant, it travels through the galaxy, it merges with other gas and dust traveling through the galaxy, and eventually enough dust and gas gathers in one place once again to be able to form new stars and begin the cycle all over again. Okay. So this gigantic cosmic recycling is really, truly the story of stellar evolution from start to end. Okay? So I think that's all I'm going to tell you tonight. I always like to leave you with a few things to read. Okay, so over here on the right, these two books, The Secret Life of Stars by Lisa Harvey Smith, kind of goes through a lot of the things that I've been telling you about in much greater detail, or at least in much slower detail, so you can kind of read them and ponder them and go read extra stuff and learn a little bit. The book there at the bottom, What Stars Are Made Of, are about Cecilia Payne-Gaposchkin. So Cecilia Payne, she was the person who first figured out that the stars are made of hydrogen, and that hydrogen must indeed be at the heart of this kind of stellar evolutionary process. She did it at a time in the early 1900s when women were not very prominent in astronomy. She was a very gifted mathematician and theoretician, and was kind of responsible for all this kind of deep understanding that we have about stars and their lives today. So this is a really great biography of her if you're interested in that. The book on the upper left is really a book aimed at us who are amateur astronomers. This is by Mike Inglis. Some of you, he's written several books for us that you may know about. But this one is a whole bunch more examples, not unlike the ones I gave you, of ways to look at the night sky, look at things to find things you can see in the telescope in the night sky, to trace out the history of the lives of stars just from your backyard. And so I really enjoy this book a lot. It gives you a lot more examples of the sorts of things that you and I have been talking about tonight, that you can read about and use at the telescope. And then lastly, if you're interested in the kind of extreme remnants of stars, this is probably still the best book. It's called Black Holes and Time Warps. It was written by Kip Thorne. It won a couple science writing awards. Kip, as many of you know, is one of the recipients of the Nobel Prize for the discovery of gravitational waves. And so he talks a lot about black holes in here and a little bit about neutron stars. And then there's a whole bunch of other relativity stuff, wormholes, gravitational waves, all of that sort of stuff. But for kind of learning about black holes, I still think it's one of the best books out there. Okay, so I am going to end there and say thank you so much for your time, and I will hand it back to Frank and we can take some questions.
Thanks a lot, Shane. That was awesome. So yeah, I'm going to go build a faster than light drive and go diamond mining at white dwarfs right now.
Yeah, let's do that, right?
Yeah. How hard can it be? Cool. All right, if you have questions for Shane, please use the Q&A button at the bottom of your screen and submit them there. We got a couple here. I'm going to abuse my privilege, though, and ask one myself. So what's the deal with globular clusters, Shane? Where do they come from? Why are they in weird places and stuff?
Yeah, why are they in weird places? So actually, I don't think I have a chart of this. I didn't even think to put one in. But if you have a copy of Tyrion's Cambridge Star Atlas, in the back of that, he has a plot that shows the Milky Way, and he shows you where all the open clusters are. And then he has another plot that shows you where all the globular clusters are. And what you'll notice, if you look at those charts, is that the open clusters all follow the plane of the galaxy, and the globular clusters are kind of spread out around the galaxy. Okay, and this is actually a really important point. In fact, so this year, some of you may know, is the 100th anniversary of Hubble's VAR plate, which is the discovery that the Andromeda Galaxy is actually not part of the Milky Way. It's a really, really far away. So the technique he used to measure the distance to the Andromeda Galaxy was actually used just a few years before that to measure the distances to all the globular clusters. That was done by Harlow Shapley at the Mount Wilson Observatory. And when he did that, what he discovered is that the globular clusters were not centered around Earth. They were centered around some other point in the Milky Way, which he correctly deduced was the center of the Milky Way. Okay, and so that's how we actually first measured the position of the sun in the galaxy, was by measuring the distances to the globular clusters using Leavitt's law. There's other bits about globular clusters we could talk about. They have the oldest stars in the Milky Way in them. And for a long time, they were at the heart of a big controversy in cosmology because we could calculate how old they were, and they were older than we thought the universe was. So that's an entire another story.
Absolutely. Cool. Thanks. All right. We have 2 questions from Luke Corwin and Mark Pernell, who are basically asking the same thing. You kind of teased about moving groups and how we might be able to use that to determine the history of our own sun, where it came from. So do we actually know where the sun came from and what its semblance might be?
Yeah, so I think the right answer to that is no, we don't know where the sun came from. This is a question we would like to ask. Actually, I don't know how many moving groups we actually have measured, right? I mean, the Ursa Major moving group is the most famous example because it's composed a lot of prominent naked eye stars. But this quest for what are the siblings of the sun is one that's been ongoing for some time. And we have no definitive candidates that all of us agree these are stars that were born in the same place, same time, same cloud as the sun. If we could find even one, that would be really helpful, because the kinematics, as we say, the motion that they share through the galaxy would allow us then to kind of get at least an approximate origin. And then we can use the kinds of surveys we're doing now with an instrument like Gaia. So those of you who don't know about Gaia, Gaia is this telescope that was launched in the mid-2010s that's measuring the distances, positions, and motion of the billion stars closest to the sun. Okay, so if the sun's siblings are somewhere around us and we could figure out which ones they are, we would be able to detect that motion from the kinds of surveys that are being enabled by missions like Gaia. So the answer is not yet, but I bet by the time Frank and I are old men, maybe we will. So.
That's way off, right?
It's a long ways off yet, Frank.
All right. Luke wants some more depth on that, actually. So could you give us some more details on what chemical signatures we use to identify the stars in moving groups that came from the same open cluster?
Yeah, that's a good question. Actually, did I put a slide here? I'm not sure I did. Here, if you will indulge me for a minute, let me grab the slides from another talk, because that is, I have a slide that I think will help with that. So we basically use a technique called spectroscopy. So those of you who, it's been a long time since you've been in chemistry or physics, or you never took chemistry and physics. Spectroscopy is this science where we take the light from stars, we basically put it through a prism. And when we put it through a prism, what we then do is that we split it out into this rainbow. We make these really infinite, very high resolution rainbows. And in the rainbows, you will see dark lines. Okay, and what those dark lines are is every atom in the universe, depending on what it is it oxygen, is it carbon, is it aluminum? Every atom in the universe absorbs different colors of light. And so when you look at one of those spectrums, you can determine what atoms are in the star by looking at what colors of light are absorbed in its spectrum. Okay, so that's the basic game that we play. Okay, so here's my dark universe talk. So this is, I give another talk about dark matter and dark energy, and I talk about this in there. So here, let me show you, this is an example here. Okay, can you see the spectrum of the sun?
Yep.
Okay, So this is what the spectrum of the sun looks like. Okay, so these dark lines, these were originally called Fraunhofer lines. They were discovered by Joseph Fraunhofer in the 1800s. And if you come visit us in Chicago at the Adler Planetarium, we have his original sketch of these that you can see, which is very cool. He worked this all out by hand. Okay, but every one of these lines is a particular piece of the fingerprint of a particular atom. Sodium, calcium, oxygen, carbon, hydrogen, helium, all of them, okay? But if I look at a different star, in this case, Arcturus, which you and I talked about, they're different, okay? And if I flip back and forth between them, if you pick a line and you watch it, you can see some lines get fatter, okay? That's telling you something about how much of the material is there. Some lines disappear and some lines appear. And that is material is or is not present, at least in large quantities, in the star. Okay, so this is the game we play. And this is actually the game we play with everything. We play with galaxies, we play with comets, we play with asteroids, we play it with stars. Okay, and it's all because every one of these chemical elements that you learned about in the periodic table has one of these unique fingerprints that I show you right here in this chart. That's a good question.
Yeah. And I'm going to end with one you're going to like. So,
okay.
Ryan wants to know, since the observation of gravity waves a couple of years ago, have there been any new breakthroughs with gravitational waves that we haven't heard about?
Well, if you haven't heard about them, that means I can't tell you about them because it's all top secret. So, no.
Not published yet.
So I don't remember what had happened at the time that I talked to you before, but the highlights of the discoveries up to now have been the very first detection of gravitational waves by LIGO. That was in 2015. In 2017, we made the first multi-messenger detection. So we detected a gamma ray burst that was associated with two neutron stars crashing together that we also detected the gravitational waves from. And then we detected some really big black holes that we weren't sure even existed till we detected them. So we saw two 80 solar mass black holes merge, and they made a new black hole that's like 140 solar masses. And that was something we had only speculated about, and we now know exists. So it's kind of rocked our world, as you might imagine. So LIGO's been doing upgrades, and we are supposed to start again, I think, in May. So you'll begin, if you start paying attention to the news, you can get alerts from us for when there's possible multi-messenger counterparts. You can get it on your phone. They go out that way. But all of that will start happening again approximately in May. So, keep your ears open the next year or so, and you'll start hearing news again.
Awesome. And I'll sneak one last one in from Mark here. Mark's asking, you were talking about the white dwarfs being composed of carbon and maybe even diamonds. So he's wondering, does the star reach that state through fusion or to electron degeneracy instead?
Yeah, it's the latter, right? So the key point about stars that become white dwarfs is they go through this kind of sequential fusion process where they take hydrogen and they make helium, they take helium and they make carbon. Okay, and when it gets to that carbon stage, they can't go any farther. They can't do anything more. And so then gravity takes over and it compresses the star, it presses that carbon together, and gravity just tries to crush it as hard as it can. But eventually this effect that you mentioned, electron degeneracy pressure, it stops the star from collapsing because all the electrons hate being pressed together. They're very, antisocial, and they press against each other, and that keeps gravity from crushing the star anymore.
Very cool.
Okay.
Thanks a lot for your time tonight, Shane.
Oh, thank you so much. I appreciate it. So
yeah. And again, if you have any questions that you think of later, your email address was in that first slide, and we'll have a recording of this up tomorrow for the club. So thank you so much. You're welcome to hang out, or you're welcome to go get dinner. So
I'll hang out and listen. Thanks so much. So.
Appreciate it. All right, I'm going to hand it back to Tricia for club news. And after that, we got Barbara. So take it away, Tricia.
Hey guys. Okay, so let me go ahead and share screen here with everyone. Okay, here we go. So some club news we have coming up. We have our next in-person general meeting and star party Saturday, March 18th. Keep an eye out on the group's IO page as well as our closed Facebook page for updates on that. Our new LoanerScope chair, Chris Hunt, has set up a new LoanerScope file in the group's IO page. And how you're going to find that file is you're going to go on the left-hand side of the main group's IO page. And under the Files tab, you should be able to click on the Files tab, and then about 8 rows down, look for Loner Scope file. If you have any questions about how to get a Loner Scope, or just any questions in general about the Loner Scope program, contact our new Loner Scope chair, Chris Hunt. His email is loners@cfas.org. We also have Geneva coming up next weekend. So, there we go. So our Geneva Dark Sky Nights are going to start back. We have our next night, 2-night opportunity, starting February 17th and going into February 18th. Our hope is that it's going to be clear skies on the 18th. That's our preferred day. We have 2 Geneva site coordinators for this February event, Eric Coyne, whose email is listed there, as well as Bill Castro. We are asking members to please limit their guests to 5. We are not doing this event as an outreach event, and therefore this is a closed event to members, but you are allowed to bring up to 5 guests each. The go, no-go status will be sent out prior to the event. So well before the 17th or 18th, we will have an idea of which day. If you have any further questions, go ahead and email either Eric or Bill. You see their emails there. We are not doing RSVPs, so just show up as is. And our setup time is going to be about an hour before sunset. Help wanted. So we still have 2 chairs open. We have a social media chair position that is open. And that's exactly what it sounds like, helping us with our social media, specifically our Facebook and Instagram page. We are also seeking a webmaster. If anybody is interested in helping us with our website, please contact me for either position. You can see my email there is president@cfas.org. And that's it for club news. So I'm going to go ahead and hand it back over to Barbara Harris, who's going to be doing the variable star of the month. Barbara, you there?
Yes, I'm here.
Okay.
Hi,
If you wanna take just a
everybody.
second to your screen.
Yeah. And while I'm getting set up, I wanted to remind everyone with tonight's topic that if they want to learn more about stellar evolution, that the Astronomical League has a stellar evolution observing program that they may be interested in to learn more about stellar evolution. So tonight's variable star of the month is T Corona Borealis. I want to go back. So T Corona Borealis belongs to a special class of variable stars called recurrent novae. And it's actually a very special class of variable stars because there are only 10 known members of this class of variable stars. And the difference between a recurrent novae and a classical novae is that a classical nova explodes, becomes very bright, and after it fades, you don't hear from it again as far as becoming bright again. But a recurrent novae, they go into outburst, and in a matter of 10 years or a century, they may have a recurrence again of their outburst. So T Bor is in the constellation Corona Borealis, which is a spring constellation, and it's sandwiched between Boötes to the west and Hercules to the east. T Bor is about a degree southeast of 4.2 magnitude epsilon Bor, and its baseline now is hanging around 9.9. So T Bor, since it's been observed, has had 2 eruptions. The first eruption was May, oh, sorry. I'm trying to, okay, was May 12th, 1866, and it reached second magnitude. The second eruption was February 9th, 1946, and it reached third magnitude. T-Corps is actually not one star, it's actually two stars composed of a red giant star and a white dwarf star. And what is happening in this system is that matter is accreted from the red giant to the white dwarf. And it forms what's called an accretion disk around the white dwarf. And this material is basically hydrogen. And when enough hydrogen is accumulated in the accretion disk and falls onto the white dwarf, you get a runaway thermonuclear explosion, which is basically the nova outburst. In February 2015, something started to occur with T-Corps. It had been stable for about 69 years. And then in February 2015, it started to brighten a little bit from its baseline magnitude of 10.2 to 10.3 to 10th magnitude. And it stayed at about 10th magnitude until February 2016, when it reached magnitude 9.2. So people started to get excited that something may be ready to happen with T-Corps. But unfortunately, it fell back to about a magnitude of 9.9, and it's been around that magnitude since then. So the two outbursts have been about 80 years apart, and it's been 80 years since the last outburst, or at least in 2026, it'll be 80 years. So astronomers think that there's a possibility that the next eruption is going to be around 2026 plus or minus 3 years. So we're right in that neighborhood, and we need to keep an eye on it. On the left is an AAVSO chart of T-Corps. At AAVSO, you could get a custom-made chart. This chart I had made with the 7.5 degree field of view, because I usually, for visual observing, I will observe with my 7x50 binoculars. And on the chart, you see numbers, and on AAVSO chart, the numbers are the magnitude of the stars. So 84 is actually an 8.4 magnitude star. They leave out the dots so that you don't confuse them for stars. So in this chart, here's T-Corps in the middle, and this 46 is 4.6 magnitude Delta Corps Bohr, and this 42 is 4.2 Epsilon Corona Borealis, and a degree southeast of Epsilon is T Corona Borealis. So it's actually pretty easy to get out there with a pair of binoculars, and pretty easy to find the constellation Corona Borealis and see if you can observe evidence of T-Corps going into outburst. And it's pretty, if it goes into outburst and it's similar to the previous outbursts of second or third magnitude, it's going to be pretty easy to determine that, because a second or third magnitude star is going to be pretty much brighter than every star in Corona Borealis. So it would be easy to determine if there's something new in that area. So it's real easy to do with just a pair of binoculars, is to go out there. Like, I'm a morning person, so I observe it every morning before dawn. Either I do formal photometry on it, or I just look with a pair of binoculars if I'm not really set up to do photometry. Or a lot of times I just plop a DSLR with a 50 or 85 millimeter lens, take a 30-minute exposure, and I could easily see T-core bore in a 30-second exposure. And like I did that this morning, and it looked to be about 9.7. Actually, I did a little experiment where I did formal photometry with the telescope in the observatory, and at the same time took a image with an 85mm lens. And I estimated from the picture what I thought T-core bore's magnitude was. And I thought it was 9.7. And my photometry of it at around the same time was 9.746. So you could actually get pretty easy, you could actually get pretty good of estimating the magnitude from a DSLR image. The way I learned about T-core bore was through my favorite astronomy biography of Leslie Peltier, Starlight Nights. And he was a really famous amateur astronomer. He was very interested in variable stars, and also he discovered several comets. And he spent about 25 years diligently observing T-core bore. And every night that he could, he would go out, and one of his variable star observations was of T-core bore. And the morning of February 9th, 1946, when it went into outburst, he had a cold and figured that he wasn't feeling well and should stay in bed that morning. And unfortunately, that was the morning that T-core bore went into outburst. And this is one of my favorite paragraphs in the book about that experience. He wrote that I alone am to blame for being remiss in my duties. Nevertheless, I still have the feeling that T could have shown me more consideration. We have been friends for many years on thousands of nights. I had watched over it as I slept, and then it arose in my hour of weakness as I nodded at my post. I still am watching it, but now it is with a wary eye. There is no warmth between us anymore. So I'd like to leave you with a line, the last line of one of my favorite old movies, The Thing. Watch the skies everywhere. Keep looking, keep watching the skies.
Good quote. Hey, we do have one question that came in. Someone's asking, is this a type 1a? So maybe talk a little bit about the relationship between variable stars and supernovas and how they're different.
Well, actually, T-core bore is interesting because they differ because of the mass of the star that becomes a supernova or a nova. Larger stars become supernova, and there's a limit called the Chandrasekhar limit, where if it's below that limit, which is 1.4 solar mass, it's not going to become a supernova. It would become a nova, and then a planetary nebula, and then I forgot after that. But a supernova would be a star that's starting out larger than 1.4 solar masses. And also a supernova, once it explodes, that's it, it becomes a black hole or a neutron star. If it's less than that 1.4 solar mass, it explodes as a nova. And theoretically, every nova may have the potential to be a recurrent nova. It's just that it may take centuries and thousands of years before we ever see it become a nova again. So it's still a star. It's just that it's very, very faint, and it basically is still a star compared to a supernova. Once it explodes, that's it. It becomes a black hole or a neutron star.
Cool. Thanks, Barbara. Tricia, did you want to take it back or just go straight to astrophotos?
We can go ahead and go straight into astrophotos. That works.
All right, thanks, Barbara. We'll have you back on our next Zoom meeting, which I guess will be April. So stay tuned for next variable star of the month. And let me share my screen and we'll go to our astrophotos of the months where we have photographs and sketches submitted by our members. So the way this is going to work is if I see you online, I'm just going to hand you the microphone here and let you talk about what we're seeing. If not, I have some notes here to fall back on. So first up, we have Bill Castro. Let me give you permission to talk here and tell us what we're seeing.
Yeah, hopefully you can hear me.
Yep.
This is a picture of Kimball's Cascade on the left, and wide field refractor with a wide field eyepiece. And I got the whole thing in there, NGC open clusters down in the bottom. And I compared that to the sketch I made a couple years ago on the right. And it compares favorably, but this kind of shows, remember the talk from last month's program, imaging is getting easier and easier. This is just an iPhone handheld to the eyepiece. My 31 millimeter Nagler is too big for anything to clamp onto it, so I just hand hold it. But if you're looking through that at an outreach, you might want to ask people if they want to take a picture, but it comes out pretty well. And similar to our other speaker from last month, simple image processing with whatever came with the computer, Microsoft Paint, I think it was, or Photos. And that's all I did to it. I didn't spend a lot of time on the computer. But I will say, when you're sketching it, I notice a lot more detail. You kind of, take your time and smell the roses, so to speak. So there's still a lot to be said about sketching. It's a pretty neat thing to do, both the iPhone and sketching.
Absolutely. And I think we have another one from you as well.
Yeah. And this is another iPhone smashed to the eyepiece, M41, another, these big, bright, open clusters really come out well. Again, nothing special done. I take about 5 pictures and, one of them is usually pretty good.
Yeah, these new phones coming out are just amazing. I saw something on the Interschnitzel today about the new Samsung phones, and you can actually zoom into the moon at 100x, and it looks as good as anything I've done with my telescope. It's just crazy how good these things are getting. Cool, thank you, Bill. And up next we have another one from you. Yeah.
Again, sunspots, and this is a plug for a handheld to the eyepiece. There's my little refractor that I'm using. You're going to read the details yourself, but just a quick plug: buy your solar filters now if you don't have one yet for the upcoming eclipse. They'll go quickly.
Absolutely. Very cool. We have some more solar pictures coming up soon too. So thank you, Bill.
The other thing I wanted to note is these pictures are okay, but when you're looking through the eyepiece, it is a lot sharper.
Yeah, I'm looking forward to getting into solar observing myself at some point. It's just, gosh, it's overwhelming, all the different filters out there, and the fancy ones and the fancy scopes, and it's a lot to wrap your head around. But hopefully we can have a mini program about that at some point. Cool, thanks, Bill. Up next, Luke Corwin. Let me give you the microphone.
Hi, so I'm relatively new to the group, actually pretty new, but and these are the first pictures I've actually taken with a serious camera through a telescope, other than the few attempts I've done at just holding a smartphone up to the eyepiece. So both of these are with my 8-inch Celestron Schmidt-Cassegrain with Nikon D5000 at prime focus, and this one is the Orion Nebula, which is ISO 6400 with a 5-second exposure. And I was really surprised when I took this, just how much detail and color came out. And I'm just using an Alt-Az tracking mount, so not equatorial. So this was much better than I expected.
Very cool.
And the same equipment. This is the fuzzy patch there is the Comet C 2022 E3. And this is, like I said, all the same settings, but with an 8-second exposure at ISO 1600. And these were both from my driveway in Ormond Beach, so fairly light polluted skies, but you can still tell it's a fuzzy comet and kind of see some of the green coloration. And yeah, thanks for letting me share.
Yeah, that's awesome. You know, that those first images you get through that 8-inch, that's exactly how I started too. And it's addictive, you know, like you're about to go down a very expensive rabbit hole, my friend. But
yeah, I'm trying not to spend too much money on it, but this has been fun so far.
Absolutely. Yep. Got some for myself here. So going down the rabbit hole, like I said, this is the Cone and Phosphor Nebula. And what are my notes on this? This is actually 19 hours of exposure time over a couple of years, actually. This is combining data from last year and this year. This is true color RGB enhanced with hydrogen alpha data. So it's kind of bringing out those wispy tendrils around the nebula here. And I believe that is the Christmas tree cluster in the middle there. You kind of have to stand on your head to see it, but kind of harkens back to what Shane Larson was talking about, those open clusters that are within these molecular clouds kind of being born and feeding off them. I find it interesting that, you know, sometimes they blow off the gases around them and sometimes they don't. I should have asked him about that, but it's pretty. And this is also one of those weird cases where you have different kinds of nebula in the same part of the sky. So all that glowing red gas is an emission nebula that's ionized hydrogen alpha that's giving off red light. There's also that blue reflection nebula in the middle there, right near the Phosphor Nebula, where that's reflected light from a bluish star reflecting off the gases. And we also have a dark nebula at the bottom, the Cone Nebula at the very bottom there, where gases are obscuring what's behind it and giving it a dark appearance. The Horsehead Nebula being another example of that. So really interesting part of the sky here. Also, here's my take at the so-called Green Comet, C 2022 E3 ZTF. This is about 2 hours of exposure time total from my home here in Merritt Island. We have about Bortle 5 skies here, but there was a fairly bright moon that night. So not a ton of detail on the tail, but you can kind of see it if you squint. So yay, a comet. This was taken around January 30th, I think it was. So close, but not quite to its nearest approach to Earth. And imaging it at that point was quite a challenge because it's moving very quickly across the night sky relative to the stars. So you have to do a lot of processing tricks to try to get the stars to look crisp and the comet at the same time. Up next, a few shots from Leonard Ward. I don't think he's online, so jump up and down and scream, Leonard, if you are, and I'm just not seeing you, but I'll refer to the notes that you gave me here. So these are a couple of pictures of the moon that he sent us, and well, that's really all I know. The other one he sent is apparently a mosaic, and dang, that's impressive. Look at that clarity, look at that resolution. So I'm assuming, just based on the title here, that this is a mosaic image of several exposures of the moon stitched together. And well done, Leonard, because I do not see where those stitching points are at all. That's a gorgeous image of the moon. So thank you, Leonard, for submitting that. And up next, a little bonus image here. So Bill Castro, you were talking about last month's presenter. This is a bonus image that Tim Russ sent me the day after that presentation. So we were talking a little bit about the comet last month, as you might recall, and apparently we inspired him to go out and give it a shot. So that next morning, he went out with his EV scope in his Los Angeles backyard and sent me this image the next morning. So this is Comet E3 ZTF as it appeared on January 12th, when it was much further away from Earth. But even from the light polluted skies of LA, I'm pretty impressed that he got that with just a 4-minute exposure. So little extra love from Tim Russ there. And we have John Starr. I hope you're online. Yep, let me give you the microphone.
There we go.
Yep.
Good evening, everyone. So yeah, this is a shot that I took as the International Space Station was transiting the moon at 8:26 in 26.1 seconds. And so it was a couple hours down the road in Lakeland. And so I used that online site, ISS Transit Finder, and had been waiting for a couple months to find one that was kind of within driving distance. And so I set up sort of on the side of the road in a residential neighborhood next to a church, and piqued a lot of interest, I might add, some churchgoers that came out to talk to me. It was pretty cloudy that night, but I was very fortunate that sort of the clouds parted there for a few minutes, and right as the space station was crossing, was able to get this shot. So I took this with a stock Canon ESOR with a Sigma 150-600 zoom lens at 600 millimeters at a f/13 ISO 800 and 1/1600. I took, I had it on burst mode and was really sort of pushing the limits of my camera. So I had 8 frames per second and was able to get 4 frames with the space station in here. All told, I took 54 shots and stacked those, and had 4 shots with the International Space Station and layered those on top to get this sort of composite. I processed this with PIP, Auto Stacker, and Photoshop just to crisp it up a little bit.
Amazing work. That's dedication, you know, just driving out to where that happens. And these sorts of images are always worth it. So really well done. Also well done, we have the Seagull Nebula.
Yeah, so this this Seagull Nebula was a bit longer, right? So this was 18 hours in exposure. So instead of half a second, which in the last shot, which was probably the most nervous and anxious I've ever been taking a shot, this was drawn out over several nights. I took about 225-minute sub-exposures using 3 nanometer narrowband filters. Because of that, I didn't get the really beautiful reflection. There's a bit of a reflection nebula up there around the head, which is NGC 2327. So I didn't get that because I was using narrowband filters, but maybe I'll add some RGB later. But I shot this with my ASI 2600 mm Pro on an Esprit 120 EQ6R Pro mount. And this is one of the first images using PixInsight. So I'm still very new to the program. I mentioned this to Frank in the email, but I watched Frank's video that I think he did a couple years ago. Very helpful. So if anybody wants to learn PixInsight, it's a shameless plug there for Frank's video. It was very helpful for me. So I got to about the soft stretch part, and then I finally had to move over to Photoshop and sort of finish it off in Photoshop. So I'm sort of pleased with ultimately how this came out.
Yeah, the oxygen data there is super clean. Love it. And the composition is really good too. So I love how you oriented that and framed it as well. It's that's good stuff. Thank you, John. And finally, we have Richard Wright. He is actually out in Europe traveling this week. So he sent me some notes on this one. Obviously, this is the sun. This was shot with a Skywatcher Esprit 150 with a Daystar Quantum PE 0.5 angstrom hydrogen alpha solar filter. Again, I really want to nail this guy down to give a talk on what this all means and how to get it set up. Shot with a Player One Apollo M Max camera. This is a merge of short and long exposures. He says it took a little bit longer to bring out the prominences, so it's a composite. He says that more talented friends can do this in one shot, but he's not there yet. So, well, I guess he's challenging himself. And hopefully we'll get a report from Richard next month about the Winter Star Party, where he's going to next week. And we'll find out what shenanigans are going on there. And that is it for Astrophotos. And Tricia, if you have any closing comments, I will hand it over to you.
Thank you, Frank. Well, I hope to see everyone next weekend at Geneva. Let me go ahead and do this real quick. Just a closing slide for everyone. So yeah, if you have any questions about tonight's presentation, on the rewatch on YouTube, you'll see some email links. So feel free to email us any questions, comments, suggestions you have. Again, thanks everyone for showing up tonight. And I hope to see you both at Geneva and at our next in person, March 18th. Thanks again, guys.